Friends, welcome to my channel once again. Today I shall uh, solve some Fourier series related problems, and I shall utilize one shortcut method for evaluating the integrations. You know that Fourier series involves some integration, mainly by parts. So I shall show you some technique so that you can evaluate the integrations quite easily. So uh, I shall start with this one, which I have already done. However, uh, for the ease of doing other problems, I shall prove this problem here also. So I am writing the problem, our problem today. I already have proved this problem earlier. You can watch my video on this in my channel, and so hence one by n square is equal to pi square by 6. Second problem will be 1 by 2n minus 1 square is equal to pi square by 8, and the third one will be 1 by n to the power 4 is equal to pi to the power 4 by 90. So I shall solve mainly 4 problems today. Let's see. Here fx is equal to x square, and the interval is minus pi to plus pi. So we know that fx can be represented in this form. This is the Fourier series expansion, and we know that a0 is 1 by pi minus pi to pi fx dx, an is equal to 1 by pi. In this limit I am writing this fx cos of nx dx, and bn would be 1 by pi So let's find a0 first. Fx is equal to x square here, so I have to perform this integration, and you can see that x cube by 3 so it will give 2 pi square by 3. So I have found a0. Now let's find an, which is minus pi to pi. Fx is x square, so this is an. Now this is integration by parts, so I have to abide by the Liet protocol. You know that L is logarithmic function, I indices, A algebra, T trigonometric function, and E exponential. So we have algebraic function followed by one trigonometric function. Now I have to take out x square, the algebraic function, out of the integration in UV technique. So I am showing some different technique which is quite easy. I am writing D, which stands for differentiation, and I, which stands for integration. Now let's write alternatively plus and minus signs. Firstly, I am writing x square as algebraic function should be treated as u in UV technique. So, I am writing it as under x square. I am writing x square under d, and under integration I am writing cos nx. Now, let us take the derivative of x square, first derivative, which is producing 2x, and integration of cos nx is producing sin nx by n. Now, again we take the derivative of 2x, which is producing 2, while integration of sin nx by n is producing cos of nx minus cos of nx by n square. And further derivative of 2 produces 0, and integration of this thing will produce sin nx by n cube. Now, I have to do this thing. Well, so this would be equal to x square of sin of nx by n minus minus plus 2x cos of nx by n square and minus of 2 sin nx by n cube. So, hope you have understood the thing. So, you can check that sin n pi will be 0 and sin minus of n pi will also be 0. So, this term will be 0, that sin involved being terms will be 0, as well as this term will be 0. I have to only find the value for cos nx terms. So, I write 2 pi cos of n pi by n square minus of minus minus plus 2 pi cos of minus n pi by n square. You know that cos of minus n pi is actually cos of n pi, as cos x is equal to cos minus x. So, I am writing it is basically 4 pi minus 1 whole to the power n by n square. As you know, cos n pi is minus 1 whole to the power n. So, I am finally getting 4 minus 1 whole to the power n divided by n square. This is our an. Fine. Now, let us find bn. X square sin nx dx. Again, we will abide by the Liet protocol and write d and I here, plus minus x square 2x 2 and 0 and sin of nx minus cos of nx by n, further integration of this term. So, sin of nx by n square and ultimately positive sign cos of nx by n cube. So, this this and this is equal to 1 by pi minus x square of cos of nx by n plus 2x sin nx by n square and 2 cos nx by n cube. So, again the sin term will vanish under these limits. So, I will not calculate that, it will be 0. So, I should write pi square of cos of n pi by n minus of pi square of cos of minus of n pi, which is basically cos of n pi. So, these terms will also vanish and this term will also vanish, since cos of n pi is equal to cos of minus n pi, that is cos x is equal to cos minus x. So ultimately this will produce 0, hence Bn is 0. So we can write x square is equal to a0 by 2, a0 was 2 pi square by 3, so I am writing pi square by 3, a0 by 2, and let's take 4 out of the sum, so minus 1 whole to the power n by n square times cos of nx. So it was our first problem, you can check it. It was our first problem and we have proved it successfully. Let's give it equation number 1, and we will be using the result or equation number 1 in deriving the other relations. So our first problem was we have to verify that sum of n equal to 1 to n 1 by n square is equal to pi square by 6. So in equation 1, let's put x is equal to pi, hence pi square is equal to pi square by 3 plus 4 of sum of n equal to 1 to infinity minus 1 whole to the power n cos of n pi by n square. That means equal to pi square by 3 plus 4. Now cos of n pi is minus 1 to the power n, so minus 1 to the power n times minus 1 to the power n and n square. So you can understand that it will produce 1 by n square ultimately. Right, or pi square minus pi square by 3, that would be 2 pi square by 3 times 4 is equal to 1 by n square, or summation of 1 by n square is equal to pi square by 6. So we have proved this, we have verified this. So problem number 1 is done. Now we have to verify that 2n minus 1 whole square is equal to pi square by 8. Now let's write this. You can see that this is basically 1 by 1 square plus if we put 2, then it would be 1 by 3 square, then if we choose n equal to 3, then 1 by 5 square, then 1 by 7 square, and so on. So all these terms are odd numbers. So I can write this 1 by n square, which involves even and odd numbers, minus of only the even numbers. So we can write this now. Let's give it equation number 2. Now from equation number, say I have to use this one. Now say this is 1. Now from 1 we have got let's 1 by n square is equal to pi square 6 into 4, or sum of 2 of n whole square n equal to infinity is equal to pi square by 24. Let's give it to 1a. Okay, let's give it 1a using 1a and 1 in equation 2. We get 1 by 2n minus 1 whole square, that was 1 by n square. You can see that I am writing that pi square minus 6, and this is pi square minus 24, so that would give you 24 4 pi square minus pi square, that is 3 pi square by 24, or 1 by 2n minus 1 whole square is equal to pi square by 8. And we were supposed to prove this also, and hence we have also proved this. Now our next problem is we have to verify that 1 by n to the power 4 is equal to pi to the power 4 by 90. We have fx is equal to x square, and the region is this. Clearly f square x, which is x to the power 4, is okay. Now if fx and f square x are integrable in an interval, then using the Parseval's theorem, we can write 1 by pi minus pi to pi f square x is equal to a0 by 2 and a square plus of where a0, an and bn are found from Fourier series expansion, and a0, an, bn we already have found. Here clearly x to the power 4 is integrable in this region, in this interval, so we can write that 1 by pi minus pi to pi x to the power 4 dx is equal to a square by 2, and our square was 2 pi square by 3, so its whole square divided by 2, and n is equal to 1 to infinity. N was 4 minus 1 to the power n by n square, and bn was 0, so we don't need to do anything here, it would be 0. So 1 by 5, and if we perform this integration, it will give this equal to 4 pi to the power 4 by 9, and there will be half, so this will be like this. 16 minus 1 whole to the power n, its square would be 1, so I am writing this, and it would be pi to the power 4 by 5. So let's change the side, equal to 16 1 by n to the power 4, and this, or pi to the power 4 45, 9 minus 5 is equal to 8 times 1 by n, this one, pi to the power 4 45 into 8 is equal to this, or 1 by n to the power 4 is equal to pi to the power 4 by 90. So we have also proved this using Fourier expansion as well as Parseval's theorem. So you can see that I have proved all the problems here. I have where is the problem? Yeah, I have proved this one. This problem is also been has been also proved. This is also proved, and finally I have also successfully proved this one. Moreover, I have used shortcut technique for performing tedious by parts integration. You can see that using this method I can solve the by parts integration quite easily, and if you do it yourself also, I think that you will also be able to perform the integrations quite easily. It will substantially reduce your time. It will substantially reduce your effort, and you will finally get the correct result. So I highly recommend you to learn this technique. It's very easy. If you practice, it would be very fine, and I reckon you have understood everything whatever I have shown here. So if you have found this video useful, if you have found if you have liked this video, then please click the thumbs up button and share it with your friends so that they can also be benefited. And moreover, you can check my channel. You can check different videos are there. You can check my channel in different topics, various topics. You can find videos starting from electrochemical workstation, research data analysis, XRD data analysis, LaTeX videos, LaTeX tutorials, vector analysis, many things, trains. You can find many things. So please don't forget to subscribe my channel and just explore my channel. Thanks a lot for watching my video. Goodbye.